Good afternoon. My talk is about parallel computing of SNiPER based on Intel TBB. At the beginning, I will introduce the SNiPER framework. SNiPER is the abbreviation of software for non-collider physics experiment. It's a general purpose offline framework, and it's very lightweight and simple to use. Now the framework has been applied to Juno and Lasha, and it performed well for this experiment. There are also some other users, potential users, such as CSNS and CPC. Here, the Juno is a neutrino observatory, and Lasha is a cosmic ray experiment, and the CSNS is a spallation neutron source located in China. This page shows the evolution of the SNiPER framework. Here, I'd like to express my thanks to the Gaudi framework. There is a long history for me to use Gaudi in the battery and database experiment, and I learned a lot from Gaudi. In about 2012, we developed a new framework, LAF from scratch. It's a very simple framework, and it's only used for the database data analysis. There are some features that fulfill the specific requirements of database. And about 2013, we expanded LAF and renamed it to SNiPER. Then we implement more and more new features in it, and enhanced its utility for general purpose. And now it can be applied to more experiments besides the Juno. The key features of SNiPER, it's implemented by the hybrid programming of C++ and Python, where the C++ is used for fundamental modules to ensure efficiency, and Python is used for friendly and flexible configuration. It supports dynamic loading and configuration. Here is some main fundamental concepts of SNiPER. The algorithm and the service, the concepts are learned from Gaudi, and the task and incident is used for flexible event processing controlling. The data buffer is used for the data memory management. I mentioned there are specific requirements for database experiment, and so is Juno. The Juno detector consists of 3 sub-detectors: the central detector, water Cherenkov, and the top tracker. Each sub-detector is triggered separately. And in the central detector, the neutrinos are detected where the anti-neutrino inverse beta decay. In this reaction, the positron and the neutron are triggered separately too. So there are 2 main challenges to it. First, the physics event number is different from triggers number or the logical event number. And second, It's mandatory for us to handle the logical event correlations. So in SNiPER, we implemented the task. The task seems like application manager. Each manages its own algorithms and services. It also manages its own data memory. But in SNiPER, the task is not application manager. Because there can be more than one task instance in a job. And a top task can own more than one subtasks, and all task instances can interact with each other via incidents. In this way, each task acts as a subroutine, so that we can handle a different number of events on demand. In this page shows the data buffer in SNiPER. There is a time window in data buffer. And during the event loop of a task, there is even a cursor moves forward one by one, and it is called the current event. The time window is revised according to the timestamp of the current event. Some other events near the current event can be loaded or trimmed automatically according to the time window. This time window is the time window size is configurable, and in this way, because multiple events are available in the buffer, so we can perform the event correction analysis. Only serial computing is supported in the original SNiPER, but we began the parallel computing this year, and the development and testing is ongoing. Here is our goals for the multi-threaded computing. First, it should be transparent to users. That means there are only a few, very few constraints to user algorithms, so that we can minimize the migration costs from serial to parallel computing. Second, it should be compatible with both serial and parallel user algorithms, so that advanced users can implement their own parallel algorithms with different methods, such as TBB, OpenMP, or row threads. Third, it should be non-invasive to SNiPER kernel modules. The parallel features are implemented in the wrapper of the kernel. And we can apply serial computing as before without the wrapper, so that users can smoothly switch between serial and parallel running mode. In order to achieve our goals, we made some top-level concept design. We'll use the event-level parallel processing, and we can create shared local SNiPER task copies to suppress the conflicts. And we will implement it based on the Intel TBB library. Here we can see there is a coincidence in both SNiPER and TBB. There is a class named task, but SNiPER task has an uppercase T. Then we can bundle a TBB task with a SNiPER task, and each event can be pointed to a TBB task. Then events are processed simultaneously in different SNiPER task copies, then invoked by the TBB task. This picture shows the multi-threaded structure of SNiPER. The master means a multiple SNiPER task scheduler. It's a non-invasive wrapper, and in each working thread there is a SNiPER TBB task, which is used to bind a SNiPER task to the TBB task, and the global resources are managed separately. And this page is the data I/O concept design. Each I/O stream is handled by a separate input or output task. There is a global buffer for each I/O stream. On the task side, there is a local buffer in each task copy. In each local buffer holds a portion of events from the global buffer. So the global buffer is bound to I/O streams. It caches all events in the memory, and we can also keep events in right order for output with the global buffer. This is important for us because our event correlation analysis depends on the event order, and the local buffer. The local buffer is just the same as the serial version of data buffer. When we execute SNiPER with master, the master breaks the serial event loop into concurrent TBB tasks. The data I/O is handled in a separated TBB task to improve the performance. And in the process tasks, there is no change for the processing procedure of each event. In this, with the SNiPER master, we can see it is transparent to the most algorithm developers. In TBB, there are many features for performance optimization. Recycling. In our case, the event processing tasks can be recycled all the time. So we can allocate all the processing tasks according to the number of threads at the beginning, and release them at the end of the program. And the schedule bypass feature. By schedule bypass feature, we are able to switch processing tasks and I/O tasks manually within rich context information. And now for in the SNiPER kernel, we revised the potential conflicts in multi-threads, and for the SNiPER master, we implemented the non-invasive wrapper, and we can perform unit-level parallel protection with it. However, there are some I/O problems. For we are still using root file, and so there are conflicts for concurrent reading and writing, and also conflicts with our data reloading scheme. And we will move to root 6. Perhaps that will be helpful to us. Here is the performance test for the ARO issue. We use a dummy algorithm without I/O. On a PC with a 4-core CPU, we can see there is a good speed up ratio with multi-threads, and expected, the performance reached the best with 4 threads. Summary. SNiPER has been successfully applied to several non-collider experiments, and the SNiPER master is implemented based on Intel TBB for multi-threaded computing. There is also a poster presented by Tao. It's about the parallel journal simulation software based on SNiPER. Now we are pushing the I/O features according to our design. That's my talk. Thanks.
In slide 9, you say that advanced users can write their own kernel using TBB, OpenMP, row threads. You write something like this, right? If you go to slide 9, number 9. Yeah. So I think that is a really bad idea. No, I mean, okay, if you write parallel algorithms using TBB, it's fine. But if you start mixing OpenMP, the scheduler of OpenMP, with the main scheduler, which is in TBB, or you create row threads, you end up with n squared number of threads. Your computer will blow up.
But we provide a chance to users. Users can implement several algorithms or anything they like. We just provide a chance.
No, what I'm saying is that you should provide the chance to do parallel algorithms using TBB, not using OpenMP or row threads. Because your main scheduler is TBB.
Yeah.
And if you add the OpenMP scheduler inside a TBB thread, that will spawn other threads, and that will grow a lot.